Hello, and thank you for being interested in our work. I'm Benoit Dora, Senior Director of Systems and Projects at Rohde & Schwarz in Munich, Germany, and I'm going to talk today about enabling electromagnetic near and far field characterization of vehicle integrated antennas using augmented over-the-air techniques. Modern vehicles are equipped with a large number of wireless communication technologies. And the transceivers supporting these technologies can be integrated in variable conditions within the car. Some of these conditions may make it very complex to test for the performance or the regulatory compliance of these transceivers when integrated. In addition, the number of tests may multiply when considering several real use cases. Just take this example where one might be interested in positioning Wi-Fi and Bluetooth antennas within the car to optimize the in-car connectivity. Well, the first question is, how do you characterize for the performance and for the field distribution within the car? And the second question is, how do you take into account all possible real use cases where there might be several passengers within the car in different positions, so on and so forth. We believe that for managing to solve all this problem, there is a need for more advanced antenna measurement and over-the-air techniques that will enhance the testing times and will enable representative assessments, eventually make practically unfeasible measurements feasible. And with this presentation, we introduce what we think is a solution to complex automotive electromagnetic characterization problems with the augmented OTA technique. There are basically two ways to characterize an antenna near or far field: experimental or numerical. When you perform antenna or over-the-air measurement, there are some advantages. A measurement is blind. There is no need to know what's inside the device under test to characterize it. You just get it to transmit or to receive, and then you have your measurement instruments all around and collect the data. It's a full system characterization. It includes eventually the transceiver within the device under test, and it includes all production and operation tolerances. But obviously there are some limitations that you are typically within canonical test environments like an anechoic chamber that simulates free space. Not every single type of field distribution can be measured. Some fields may be very difficult to access by just probing. And time may explode if you have a lot of configurations to actually measure. And simulation, well, you definitely have some advantages that very complex scenario can be simulated. You are basically not limited by any scenario complexity, and you can assess every field distribution within this environment you're simulating. Also, you have parametric modeling and batching, which allows to run simulations around the clock and test a huge number of configurations very efficiently. But there, the limitations is that to simulate an antenna integrated in a complex environment accurately, you need to have very deep knowledge of all of this antenna and its environment. You would not also be able normally to simulate the complete system, like no active circuits, for example. And the modeling of production tolerances will be very cumbersome. But the idea behind augmented OTA is that if we could combine the best of antenna measurement and electromagnetic simulation, then we would get a very powerful technique to solve all kinds of problems without having to know what's inside the device on the test. The way to achieve the convergence between the numerical and the experimental worlds is through the equivalence principle. This principle tells you that if you have a radiating source here, radiating E and H fields outside a surface A encompassing this source, then these E and H can also be seen as generated by an equivalent source of electric and magnetic currents flowing over A. If one imposes a boundary condition within A, then these currents are uniquely determined. And the way to obtain these currents is typically by measuring the field. It can be two components of either the E or the H or a combination of both orthogonal phasor fields on a surface, and then solving an inverse problem to determine the currents that would give the field over the measurement surface. The method that we use in our work to solve this inverse problem is called the FIAFTA, the Fast Irregular Antenna Field Transformation Algorithm, developed at the Chair of High Frequency Engineering of the Technical University of Munich. And you see how it formulates mathematically in the form of this FIAFTA operator, which relates the voltages measured at the test probe to the electric currents and the magnetic currents flowing over the surface A. And you see here these kernels in the integral being the electric and magnetic green functions. I will show you now how the equivalent current reconstruction is actually the cornerstone of the augmented OTA technique, of which I am presenting you a flowchart here. So the way it works, like we said, it starts with a measurement of at least two orthogonal electromagnetic field phasor components around the radiating module. Typically, we would perform the measurement of a radiation pattern, two electric field components over a sphere. It can be achieved by a distributed access system like this, where you have the device on the test and the test probe there, and then you obtain your radiation pattern, and you would have this in amplitude and phase for at least two components. The equivalent source calculation is here, and this is what I call here the processing bridge, where out of these pattern measurements, we can reconstruct, using the FIAFTA, the electric and magnetic currents over a surface closely encompassing the source. And the third part is to simulate a virtual scenario in which we import the equivalent source in a full wave software, and then we compute the electromagnetic quantities in the modeled scenario when all the scatterers are brought around the equivalent source. So this is in our work done with the software Empire XPU from IMST, and here you can see, for example, that we brought the source into a car model completely integrated, and we will discuss in more detail this example. There are so many possible applications of this augmented OTA technique in the automotive world. We already talked before about this example of in-car connectivity characterization optimization. Well, you could imagine to solve this problem by taking an antenna, Wi-Fi Bluetooth antenna, to be measured within a near field or far field range, and then out of this measurement reconstruct an equivalent source, and then integrate this equivalent source in a virtual model of the car to then calculate the field within the car. This example here is about evaluating the performance of a communication antenna integrated behind the windshield within the rearview mirror of a car. We will detail this example in the next slides. Another case you could think about is having an antenna which would be vehicle mounted, for example, and you want to evaluate the exposure of a bystander or eventually of a passenger of the car. Let's look in more details in this just cited example of a 5G millimeter wave antenna array integrated in the rearview mirror behind the windshield. You can see the front side of the device here. This is the physical device, and the numerical model of the device backside modeled in Empire XPU FDTD software. This array is a 8x8 multi-layer antenna which operates in Ka band, and as you can see from the backside here, it has a 1:8 divider and 16 beamforming chips with each of them individual amplitude and phase control. And with these chips, it allows to perform beam steering. As IMST designed and manufactured this array, we have then access to completely the physical model and the numerical model. And it's perfect because we can then compare the augmented OTA technique, which is hybrid between measurement and simulation, versus the 100% full wave modeling as a reference case. For performing the measurements, we used our fully anechoic chamber ATS1000 equipped with a distributed access system that you see here in more details, where you have the test probe. It's a dual polarized Vivaldi antenna mounted on this arm, which rotates in elevation. And here you see the device under test mounted on an azimuth pole. So that rotates in azimuth, that rotates in elevation to cover the full sphere. And the separation distance here is about 50 centimeter, where the array is placed at the center of the coordinate system via a laser alignment capability. The two ports of the probe are connected to a vector network analyzer through a rotary joint here, and as well as the input port of the array is connected to the other port of the vector network analyzer, and here we use the ZNA43. We carried out measurements at 29 GHz with a 2-degree angular sampling rate. I'm showing you now the near-field results that we obtained after then extracting the equivalent source and then integrating this equivalent source in the model of the car. You can see here the cut plane that we are looking at. And these are the field. This is the E field at 29 gigahertz in magnitude. And now you can see a comparison between the augmented OTA technique, so the combination of measurement and simulation, where the source here is the equivalent source, and here you have the reference simulation, which is 100% made of the numerical model of the antenna integrated in the numerical model of the car. You can see that the distributions are matching rather well. Obviously, in the very vicinity of the antennas, there are more differences, but here we have the same scales, and you can see how close the values are. One thing to notice is that the computational performance of the equivalent source-based simulation is much better, where the reference simulation necessitates 3.6 gigacells in FDTD, 108 gigabyte RAM, and an 180-minute simulation time. Because we don't need to model the fine details of the antenna when we do the hybrid approach, then the number of mesh cells is much lower, as well as the RAM usage, and the 180 minutes become only 15 minutes of simulation time. We also looked at the far field, and here you can see that we computed the directivity patterns in two orthogonal cut planes, basically phi equals 0 and phi equal 90 here. And in black you have the reference simulations, fully numerical, and in red the results of the hybrid approach. Well, obviously there are some differences, like you can see, especially in the secondary lobes or in the lower energy regions of the pattern. But the main beams are pretty well aligned. There is also a difference in the amplitude of those beams, but all in all, we have a reasonable agreement. And especially when you consider that there are DUT production tolerances which are not taken into account in the numerical model, as well as tolerance on the electronics, and there is some modeling uncertainty because not all the parameters are perfectly known. So somehow we can't really say whether the hybrid approach or the fully numerical approach gives the more accurate results. Now, this is something we need to further investigate, but all in all, reasonable agreement. As a second use case, I want to show you how the augmented OTA technique can apply to human exposure evaluation. Our examples get a bit away from the automotive here, but it should be pretty obvious how the conclusions and results we obtain can be extrapolated to the case of automotive. In human exposure evaluation, we're typically interested in assessing quantities like specific absorption rate below 10 gigahertz or free space incident power density, which I call PD in the next slides, above 10 gigahertz. A state-of-the-art approach to measure those quantities is to use the 6-axis robot with a diode-detected probe, which is moved typically in a phantom, which is a human head or body model for SAR measurements, or just moved in free space above the device in case of power density measurements. What we are willing to achieve here is to replace the standard near-field dosimetric measurement system by a near-field spherical scanning system, like you see here with, again, this elevation arm rotating the probe, and then the DUT at the pole rotating in azimuth. We use this system then to extract the E-field two components, magnitude and phase over a sphere, and then solving the inverse problem, calculate an equivalent source, which becomes a numerical version of our DUT based on measurements, then injecting this equivalent source in a numerical model where you have the source here and here the mannequin, the phantom, and then from full wave simulation, calculate the SAR within the phantom, so the actual exposure of the phantom. And we did this, and we published the results in the AMTA conference 2021. The device you just saw before is a low power radio base station from Ericsson with 4 antennas operating in these frequency bands. And we looked at reconstructing the SAR from measurements over the air within this range at 1.29 meter range length. We achieved rather good agreement with reference SAR measurement on the dosimetric measurement system like you just saw for 20 millimeter distance. You can see here we are around 0.4 dB maximum deviation between the SAR obtained from the augmented OTA technique versus the SAR obtained with the dosimetric assessment system. At 5 millimeter distance from the phantom, we observed more differences, and we found that the major cause is due to the power normalization. We are preparing further publications on the solution we found to mitigate that effect. Another human exposure case we looked at is for millimeter wave transmitters, where we evaluate the power density. And we also published this result in the IEEE Conference on Antenna Measurement and Application in 2021. In particular, here we looked at these antennas which are used to validate dosimetric assessment systems at millimeter wave, which is a slotted horn antenna, creating quite strange distributions. And we have models of these horns at 30, 60, and 90 gigahertz. And we compared the power density measured directly on a near-field system versus the power density reconstructed from measurements at 50 centimeter range length within the spherical scanning system, and then reconstructed at only 2 millimeter from the device under test. And there you can see that we could achieve below 3% error in so-called peak special average power density reconstructed in the vicinity of the device. I think it's interesting to show a bit more details around this power density reconstruction because it teaches us something on the augmented OTA approach. You can see a comparison for the 90 gigahertz horn with reconstruction at 2 millimeter from the horn. So this is the near field, the reference near field at 2 millimeter from the horn, and here the power density. And you can see here the augmented OTA reconstructed near field and power density based on the 50 centimeter measurements. And so they are extremely close. Okay, there are some truncation effects we see here, but all in all, very close agreement. Also on the peak special average power density, which is the quantity of relevance for exposure measurements, see the very close agreement between the reference and the reconstructed. Now the case of the 30 gigahertz horn and reconstruction of the power density down to 2 millimeter from the surface of this horn shows some interesting effects. You can see here again the near field magnitude, total magnitude of the E field and the power density. And you can see the same plots obtained via the hybrid augmented OTA technique. What you can right away observe is that there are faster spatial variations within the power density, which are not correctly retrieved from the augmented OTA technique. And this is because as we are probing at 50 centimeter away from the device under test, we are missing some evanescent components or reactive field portion from this far field measurement, and this affects the local power density reconstruction, as obviously 2 millimeter is a very short electrical distance at 30 gigahertz. It's lambda over 5. And so we found out that when we try to reconstruct from these larger distance measurement the field in the very vicinity from the antenna below lambda over 3 or lambda over 4, we see some deviations between the two. Above lambda over 3, this is actually not significant. But by the way, when we are looking at the average quantities, still we have a very good agreement. And so somehow the averaging kind of takes this error out and mostly extracts the active content of the power density. One last important point. So far we talked about augmented OTA technique, but the examples we showed were based on antenna measurement with a VNA. How can we apply the augmented OTA now when the device on the test transmits digitally modulated signals over RF? Well, in the papers we just mentioned, we propose two setups to measure over the air the propagation phase. So in this setup we use for millimeter wave power density reconstruction, you have the millimeter wave DUT here, and then the test probe, instead of being connected to a VNA, the two poles get through a RF switch and then to a down converter. We also put an antenna near the device under test, fixed with respect to it, and that antenna conveys a so-called phase reference signal. We have the two down converters here synchronized on the same LO so that they are phase coherent, bringing the signal to IF and then connecting those two IF signals to an oscilloscope with phase coherent ports. And having phase coherent ports at the oscilloscope allow us somehow by comparison of the two signals to remove the influence of the modulation on the phase and extract the phase difference that comes from the propagation only. A similar concept was applied for sub-6 gigahertz measurement, but instead of using an oscilloscope in this particular case, we used two IQ receivers that we synchronized on the same LO. And this plot here shows comparison between the measurements we obtain in magnitude and phase over the sphere for a given DUT when measurements are made with a VNA, or when measurements are made with the IQ receiver and a TDD5GNR test model 3.1. You can see that these are really comparable. Here you see a lot more noise, That was because our system was not so well optimized for good dynamic. Cables were really long, but this is something we can improve in the future. And the concept, however, was proven to work. In conclusion, I introduced the augmented OTA technique, which uses the equivalence principle or the equivalent current reconstruction to create a numerical model of a measured radiating source and then be able to inject this numerical model into a more complex virtual environment where one can then assess practically unmeasurable conditions. We demonstrated promising results of this technique on example applications, even in the case where virtual scatterers are brought in the very close vicinity at fractions of wavelengths from the antenna. And in these cases we looked at, there was, for example, this antenna integrated in complex conditions in the rearview mirror of the car. We also showed human exposure evaluation aspects, which were not on automotive cases, but you could imagine how this extrapolates to automotive, measuring an antenna, creating the numerical model of this antenna, integrating this numerical model in the car, and then evaluating the exposure in the passengers, for example. The applicability of this technique was also established in the case of digitally modulated TX signals, where we presented systems capable of OTA electromagnetic field phase measurements. We showed important sources of reconstruction errors that were identified. One is relating to the power normalization in the numerical modeling stage. This is something that we will address in future publications. We also showed that very near field interactions may not be entirely reproduced by the augmented OTA technique, and that would depend on the reactive field information that is captured at the measurement stage. Obviously, this effect can be mitigated by using more near field techniques at the measurement stage, or may not be so important depending on the type of quantity we want to assess. And we saw this on the power density case. For future work and publications, we are working now on this new approach to power normalization. We also are working on new use cases, like we will have more details on an in-car connectivity performance and passenger exposure evaluation example. And we are also working on more systematic evaluation of uncertainty contributors. With this, I would like to thank you for your attention, and these are a few references where you can find more details about our work. Thank you.